Welcome to my presentation. Today, I'm going to show an exploitation on Apple Mac device, just from one click to complete takeover. First, let me make a brief self-introduction. I am Mickey Jin, a security researcher from Trend Micro. My main job is to analyze some malware and hunt for zero-day vulnerabilities. Now, I mainly focus on the security of Apple products. Over the past 2 years, I have submitted over 100 reports to Apple and got more than CVE credits from them. I really enjoy reversing and debugging. And this is my Twitter handle, Patch1T. Welcome to follow me on Twitter. Thanks. Okay, here is my agenda. First, I will explain the motivation to dig such an exploitation. Then, I will cover some related attacks in the real world. Next, I will talk about the challenges I encountered and how I overcame them. Then, there are the details of the vulnerabilities I discovered for this exploitation. I will provide an awesome demo by chaining these bugs together. Before the end, I will share another vulnerability which I discovered during the research. Finally, I will make a summary and share the code repository. So, why do I want to dig such an exploitation? The reason is simple. Apple offers generous bug bounties for exploitations. Here, exploitations can be divided into two categories, one click and zero click. And Apple has already given the definitions. One click refers to an exploit requiring user interaction to successfully gain access or execution. For example, the user clicks a malicious link or opens a malicious file. Zero click refers to an exploit requiring no user interaction to do that. For example, being on a network or in proximity is sufficient. Sensitive data refers to some privacy items that should be protected by TCC, such as contacts, notes, photos, and so on. So, you might be wondering, is there any related attacks before? Next, let's take a look at some classic cases about zero click and one click in the real world over the past few years. Here are two zero click attack cases. The first one is about iMessage exploitation. This is a classic research by Samuel Grob from Google Project Zero. The root cause is a memory corruption issue in the NS on Archival API, triggered by the deserialization of iMessage data. After exploiting the bug for remote code execution, he attacked the non-sandbox process to escape the sandbox by reusing the same bug. Finally, he pawned the iPhone remotely by sending some crafted iMessage data without any user interaction. The second case is the Pegasus spyware, which is developed by NSO Group and disclosed by Citizen Lab. It used at least 2 0 days in the attack. The first one is CVE 2021-30860. It is used for remote code execution. It is a very common integer overflow vulnerability in the core graphics framework, triggered by passing JPEG2 stream in PDF from a message attachment. But its exploitation is really advanced. In order to bypass ASLR and PAC, it builds a Turing-complete machine inside a PDF document file. And the second 0 day is CVE 2021-31010, which is used to attack the non-sandbox XPC service to escape the sandbox. Finally, the attacker can also take full control of the target's iPhone without any user interaction. Next, here are two one-click attack cases. The first one is a watering hole campaign, which is discovered by Google TAG. It used an end day and a 0 day in its exploitation. CVE 2021-1789 is the end date for remote code execution. This is a JIT compile optimization issue in WebKit, triggered by opening a web page with a malicious JavaScript payload. And then CVE 2021-30689 is the 0 day for local privilege escalation. It is a port type confusion vulnerability in the XNU kernel, triggered by the XNU system call MacMessage. The second one-click case is about GateKeeper bypass. The blog post titled "All Your Macs Belong to Us" gives the details of CVE 2021-30657, which is actively exploited by malware Slayer in the wild. It bypassed macOS file contain, GateKeeper, and authorization requirements. Once a user opens a fake document, it is pwned. After studying the old classic cases, now I want to dig a one-click exploitation by myself. Here is my summary of the flowchart of the challenges that need to overcome. First, whether it is a zero-click attack or a one-click attack, the goal is to gain the ability to run arbitrary code remotely on the target machine. Of course, the execution permission at this stage is often very low, and we will likely be restricted in an application sandbox. So next, we usually need to find a vulnerability to escape the sandbox and gain privilege escalation through another vulnerability. Our final goal is to execute arbitrary kernel code. Kernel code execution is the highest privilege of the operating system. So, if we can break the kernel, then we are the king of the target machine. In addition to this, there are two macOS-specific vulnerabilities. They are SIP bypass and TCC bypass. I will discuss them in detail later. So, these are the vulnerabilities I discovered for the exploitation. First, I exploited CVE 2022-22616 to bypass the protection of macOS GateKeeper to get the ability to execute code remotely. Then I will get root privilege escalation by exploiting CVE 2022-22639. Next, I will bypass the system integrity protection to modify some critical system files by exploiting CVE 2022-26712. Finally, I can get arbitrary kernel code execution with the SIP bypass primitive I got. However, the last one is related to another unpatched 0 day, so I couldn't share the details here at this time. So the first step is to get a remote shell. Here, I will exploit a GateKeeper bypass issue to achieve it. Okay, let's take a look at the details about macOS GateKeeper. It is designed to ensure that only trusted software runs on your Mac. For apps from the App Store, Apple reviews each app before it is accepted and signs it to ensure that it hasn't been tampered or altered. For apps outside the App Store, there are three security features for the protection: file contain, GateKeeper, and authorization. File contain is a security feature introduced in OS X library. When a user first opens a downloaded file, such as an application, file contain will pop up a warning dialog to the user that requires explicit confirmation before allowing the file to execute. The idea is to ensure that the user understands that they are indeed opening an application, even if it looks like a picture or document. It should be noted that even if the application is signed and notarized, the file contain prompt will still appear. Unfortunately, naive users keep infecting themselves. They often ignore the file quarantine alerts. Then Apple introduced another security feature, GateKeeper in OS X Lion. It is built based on file quarantine. It checks the code signing information of downloaded items and blocks those without a developer ID. If the downloaded application is not signed, it will prompt the alert dialog like this. However, malware could still be resigned with the valid developer ID. To combat this, Apple requires the legal software to be notarized since macOS Catalina. macOS developers have to submit their application to Apple for notarization. Then Apple will scan the application to make sure it is not a malware. Once approved, the application will be awarded with the ticket. The ticket tells macOS GateKeeper that the app is notarized by Apple and could be trusted. Finally, users can be confident about the software they run doesn't contain no malware. If the software is not notarized, then it will be blocked and the system will prompt the alert dialog like this. You might be wondering, how does macOS know to analyze a file in order to possibly display a file quarantine, GateKeeper, or notarized prompt? The answer is the special file extended attribute, com.apple.quarantine. All the files downloaded from the internet will be attached with the special quarantine attribute. Also, if the downloaded file is an archive, then all the files inside should also be quarantined. Note that only the applications with the quarantine attribute will be scanned by GateKeeper. If a file doesn't have the quarantine attribute, macOS will assume it as a local file. Then none of the checks will be performed, and thus no prompts will be displayed. We can use the system command xattr to access the extended attribute of a file. Here we can see that in addition to the quarantine attribute, there is another attribute that records the URL information you downloaded. macOS system browser Safari has the default feature to open save files automatically after downloading. The save files include pictures, documents, archives, and so on. In my opinion, this is a dangerous feature for two reasons. First, open files automatically makes remote attack easier because save files are not really safe. A large number of file format parsing vulnerabilities have been disclosed in history. And second, it is especially dangerous for archived application bundles because system launch service will automatically register the URL scheme in the info plist file. An attacker could then access the URL scheme to prompt the user to open the downloaded application remotely. Therefore, it is recommended to disable the feature in Safari preference when you got a new Mac device. CVE 2021-22616 is the GateKeeper bypass vulnerability I discovered. The POC here is simple. I just created an application that pops up a calculator by using a bash script and then compress it into a gzip file. After the gzip file is downloaded by Safari, it will be automatically decompressed due to the dangerous feature we talked before. And then the archive files will be trashed after the compression. We can check the quarantine attributes using the system command. Here we can see that the gzip file itself is quarantined, and the extended attribute indicates that it is downloaded by Safari. However, the inner zip file is not quarantined. And thus my POC application is not quarantined too. Therefore, my POC application can bypass all the checks from file quarantine, GateKeeper, and Authorization. It could be launched without any prompts. The root cause exists in the XPC service sandbox broker. It is responsible for decompressing archives automatically. As you can see from the onArchive method here, it writes the decompressed data directly. However, it forgets to apply the quarantine attribute. Now, the patch for the issue is also simple. It just duplicates the quarantine attribute. Okay, now we can run arbitrary command remotely on the target machine. Luckily, we don't have sandbox restrictions, but we need more permissions. So next, we will escalate our privileges. There are some known ways to escalate privileges. The first is to attack the system kernel directly. We can hunt for some memory corruption issues from the XNU kernel and the kernel extensions through fuzzing. But since some new mitigations were introduced, it's getting harder to exploit. The second is to abuse the features on some root processes, such as spawning child process, reading or writing some special files, and so on. The third is to attack some root daemon service via IPC. And there are many other ways, for example, dynamic library hijacking, abusing the SUID binaries, and so on. Here, I will try to attack a root daemon service because it is a common way and easy to exploit. I found an attractive target daemon service named SUHITB. It is a helper process for software update. It has many attractive advantages. First, it is not sandboxed. This means we don't have to take the sandbox restrictions into consideration after we compromise this daemon service. Second, it is running at the root. It means that we can get the root privilege as expected once it is compromised. Third, it has the special entitlement com.apple.rootlist.install, which grants the process special permission to bypass SIP restriction. Additionally, it exposes some IPC service routines to unprivileged clients. Last but not the least, some old vulnerabilities have been reported in this daemon service before. The main logic of the daemon process is implemented in the class SUHelper. It registers an IPC server named com.apple.suhelpd via the API bootstrap check-in. The IPC client has already been implemented in the private software update framework. The class SUHelper proxy encapsulates all the client-side interface to communicate with the IPC server. It uses API bootstrap lookup tool to open the IPC connection by the service name. There are 45 service routines implemented on the server side, and each has a corresponding delegate method from the client side. We can review them one by one to hunt for possible vulnerabilities. However, not all of them are available to unprivileged clients because the server has a rights authorization mechanism to verify whether the service request is from a legitimate client. Next, let's see how the authorization mechanism works. Before the client requests the IPC service routine, it needs to generate an authorization object through API authorization create. And then make it as an external form to transform the authorization object to the server for verification. Next, when the server receives the authorization object, it determines whether the specific rights can be granted to the client by checking the authorization object and the UID of the client. The following is an example of a service routine handling flow. First, when the client requests a service routine, it calls a specific method of the SU helper proxy class, and then serializes the request into a MAC message buffer, which is then sent to the server side by the system kernel. When the server receives an IPC request, it will check whether the specific rights were previously granted to the client. If yes, it will call the real service routine through the class SU helper. Otherwise, it will reject the IPC request. The issue exists in the special IPC interface named Prepare Install Assistant with pass. It calls the real service routine directly, without validating the client's rights. After diving into the internal implementation of the service routine, I found that it will try to load a bundle named OS Installer Setup Framework. However, the bundle path could be controlled from the IPC client. So, my first attempt was to load a malicious bundle into the daemon process in order to share its root privilege and the special root list entitlement. But I found that hardened runtime is enabled by default for system processes, and only Apple-signed dynamic libraries are allowed to load. However, if we can find an old version, vulnerable, and Apple-signed dynamic library, we can get it loaded for exploitation. My second attempt was to let it load the original framework as expected. Then I found the method startup server will be called immediately once it is loaded. In this method, since SU helper D is running as root, we will enter the else branch. Then it will submit a job in the domain of system launch D. So the job to be launched will also run as root user. Through debugging, I found the job path is an executable named OS Installer Setup D. It is inside the directory controlled from the IPC client. So we can directly write arbitrary payload in the job path to enjoy the root privilege. I put the POC and demo for your reference. Now, Apple addressed the issue by validating the client's right before calling the special service routine. Next step is to bypass the system integrity protection. System integrity protection is a security feature introduced in OS X EI Captain. It is also known as rootless. This means that even if you have root privilege, it is not enough to make some modifications. It protects the entire system from tampering from multiple perspectives. First, it denies your debugger from attaching to Apple-signed process. Second, it prevents you from modifying critic system files. Next, it prevents you from loading unsigned kernel extension. And it will also restrict some detrace actions. It is enabled by default, and it can only be disabled in recovery mode, which means a reboot is required. File system protection can be thought of as a special sandbox applied to the entire system. The configuration can be found from the file named rootless.config. Take the location /library/apple as an example. From the output of the system command ls, we can see that it is restricted, and it has the special extended attribute com.apple.rootless. And if we try to touch a file inside this location, it will return the error, operation not permitted, even if I execute the command with root privilege. You might be wondering, how does the operating system update the system files? The answer is within the special entitlements. Entitlements are embedded in the code signature of the executable when code sign. It is used to grant special permission to the executable. We can use the system command code sign to check the entitlements like this. Some special entitlements can only be used by Apple. Here the entitlement com.apple.rootless.install is only signed with a few system commands. This entitlement grants the permissions to modify system files for a special purpose, such as updating the operating system. The next entitlement is more powerful. It not only has the permission as said before, but can also be inherited by all of its child processes. So I wrote a script to scan all the executables with the special entitlements from the entire operating system, and found the following list as my candidates for SIP bypass. Finally, I choose the XPC service, System Sharp service, as my target. In normal scenario, an XPC service should check the signature and entitlements of the incoming client. In the delegate method named should accept new connection. If the incoming client doesn't meet certain requirements, then the XPC service should reject the client's connection by returning no. However, in the System Sharp service, I found that it has no validation of incoming client in its delegate method, and it always returns yes. This means that any process can make XPC request to the service. It accepts connection from clients by using SV Sharp service protocol. The protocol has only one method, named Sharp with option. So we can make a malicious XPC request to the service and ask it to help shuffle a file from one place to another place. In fact, there was already an XPC client in the system. The sharp command within the package-kit framework has an uppercase X option to connect to the privileged system sharp XPC service. So the POC is very simple and requires only one line. Invoke the sharp command with the uppercase X option to read and write the SIP protected files directly. Apple addressed the issue in two steps. First, remove the Sharp service framework, and of course, along with the vulnerable XPC service. For the system command Sharp, remove the options for XPC. The patch seems perfect, but is it enough? The old vulnerable XPC service is still signed with the special rootless entitlement. So, can I launch the old vulnerable XPC service from the new OS? If yes, it will be a bypass again. To prove my concept, I developed a new application from the Xcode template with an XPC service inside the application bundle. Then open the build application bundle directory. Replace the build XPC service bundle with the older vulnerable one. Finally, the application can launch the older XPC service and send malicious XPC requests to it to bypass SIP. After I submitted this report to Apple, Apple adjusted it again and assigned CVE 2022-32826. Now, there is no XPC client from the system, so I have to implement the XPC client by myself. Here is the code. First, create an XPC connection using the XPC service name. Then set the remote protocol. And finally, call the special XPC service routine with the connection proxy remotely. Now, the patch is adding an additional validation for the auto-sign executable in the AMFI kernel extension. It prevents the old vulnerable XPC service from launching. Finally, I can get arbitrary kernel code execution via the SIP bypass primitive I got. Unfortunately, I couldn't show it here right now due to another unpatched 0 day. However, we can directly bypass the TCC protection via the SIP bypass primitive to access the user privacy. TCC is short for transparent, consent, and control. It is a security feature introduced in macOS Mojave. It is designed to protect your privacy from the following items, such as microphone, camera, address book, private photos, and so on. You can set the privacy permissions for each application from system preferences. This is an example of the TCC prompt when some application wants to access your address book. In fact, all users' configuration data is stored in SQLite database named tcc.db. There are two locations. One is for the global, which is restricted and SIP protected. We need the rootless related entitlements to modify it. And the other one is for each user. It is protected by TCC itself. We need the full disk access permission to modify it. From the access table of the database, we can see the service column lists the specific TCC permission items. The client column is the bundle ID or absolute path to the request target. The auth value column is the decision. 0 means denied. 1 is unknown. 2 means allowed. There are two TCCD daemon services running on the system. One is for the global, running as root. The other one is for each user, running as a normal user. The daemon process is responsible for validating the entitlements held by the main executable and handling all kinds of XPC requests. It will query the database to decide whether the requested TCC permission can be granted to a specific process. And it will also update the database when user changes the TCC configurations from system preferences. It has the ability to modify the protected database because it has the special rootless entitlement. There are some special entitlements for TCC2. The entitlement TCC allow grants the permission to access the TCC items directly without prompting the user. The value for the entitlement key is an array, which lists all the TCC permissions it has. When it needs to access the corresponding TCC item, TCCD daemon process will approve the access request directly without querying the database. The second entitlement, TCC manager, allows the client to request the TCCD daemon service to update the TCC database. There are many ways to bypass the TCC protection. We can directly exploit the design flaws of the TCCD daemon. And the most frequently used method is abusing the special TCC entitlements mentioned earlier. Moreover, there is an awesome black hat topic related to TCC bypass. The link is here. You can learn more about TCC bypass from their presentation slides. Here, I just modify the protected database directly to bypass TCC with the SIP bypass primitive I got. Now, let's watch the demo. First, let's take a look at the file directory structure on the hack server. Then using Python to start a HTTP server. I have created a clean virtual machine using the app. We can check the target system version. And the SIP status is enabled. Now, the temp directory is empty. Checking the TCC configuration in the target system. No application has been granted any TCC permissions. Now, the victim is trying to access the phishing URL. Safari is downloading the gzip file from the phishing URL and automatically decompress it after downloaded. Currently, no nc command is running. Now the victim is trying to open the downloaded fake image. It will open a real image and create a reverse shell. Now the attacker connects to the reverse shell to execute arbitrary commands as a normal user. The next stage payloads and the configuration have been deployed to the temp directory. Before executing the LPE exploit for root privilege escalation, we can check the target system. Now, no launch daemon registered and no root shell. Now, running the LPE exploit. And exploit successfully. The LPE exploit registers a launch daemon named com.demo.reverse shell and drops an executable named root shell. The reverse root shell will connect to the hack server on port 1337. Creating a hack server listening on port 1337. Then the reverse root shell connection is successful. The hack can run arbitrary commands as root, trying to touch a file in a root-owned directory. And the file touched successfully. trying to access the private desktop directory, which is protected by TCC. But no permission. Now trying to take a screenshot on the target machine. And the captured screen is empty. Checking the TCC configuration in the target system. Root shell is not granted any TCC permissions. Now replacing the protected TCC DB via the SIP bypass primitive. Exiting and restarting the reverse root shell for the TCC configuration to take effect. Now we can see the root shell has got the TCC permissions. Restarting the hex server on port 1337. Trying to access the private desktop again. And we can get the secret files inside. And try to take a screenshot again. Screenshot successfully. And you have been hacked. Okay, let's back to my slides. Before wrapping up, I would like to share another vulnerability to bypass TCC, which I discovered during my research. Now, let's recall the daemon root process SUHITB we talked about earlier. It has the special root list entitlement, and this means it has more privilege than full disk access permission. There are 45 service routines, and although most of them require root authorization, they are still great targets for TCC bypass. The issue exists in the service routine named registered personalized manifest for product key in foreground. It is only available to root IPC clients. Note that the parameters manifest directory and the product key can be controlled by an attacker. And then the service routine will copy the files from the manifest directory to this location. The red paths are controllable. So I have two exploit ideas. The first is to make a malformed product key for path traverser in order to overwrite arbitrary SIP protected files but it failed because there is a sanitization for the product key. Here in the function, it checks for special characters to prevent path traversal attacks. My second attempt was to have the manifest directory point to a TCC protected location. The daemon service can read the TCC protected contents due to its entitlement. Then, the service will help me copy the TCC protected contents to the destination path, and the destination path is readable by everyone. The POC is simple with a few lines of code. After generating the root authorization, we can access the IPC service routine to register personalized manifest for product key. Then, have the manifest directory point to a privacy location. Finally, the privacy data will be copied to another location that we can access. We can also watch the demo video. The SIP status is also enabled. Trying to access the address book directly from the terminal. And don't grant the terminal TCC permissions to access the address book. Running the exploit program to steal date from the address book. Then we can read the address book data from the directory. Okay. Let's come back to my slides. Now the patch is adding entitlement checks for the incoming IPC clients. The requesting client must have the entitlement com.apple.private.sqhelpd. Okay, let's make a summary. From the previous cases, we will now realize that Apple systems, including macOS and iOS, are not as secure as we thought. So remember to keep your device up to date. And don't click on the URLs from untrusted strangers. And don't use pirated software. Watch out for the children inside. Next, for security researchers, I think logic bugs are very powerful. They are easy to exploit and can work across platforms, both on Intel and ARM platforms. You can get more by chaining bugs together. The source code of my exploit chain was submitted to the GitHub here for research purpose only. Here are the links for your reference. And thanks, that's all.
Thank you. If anybody wants the links, the slides should be uploaded in the next few hours or by the day. So you don't have to take a picture, it'll be online. We've got a couple of questions. Tim Apple. Is there an easy way to run arbitrary programs in the macOS sandbox? It would be nice if Apple made sandboxing easier for regular users running untrusted apps that don't opt into the sandbox.
Running arbitrary programs in sandbox within the sandbox restriction. There is a case to attack the system kernel from sandbox directly. So some Mac service can be accessible even in sandbox. The sandbox configuration is in a config file. So it is possible.
So by editing the config file.
Yeah.
Okay. Is Tim here? No Tim Apple? Okay. And Anonymous, great talk. Your presentation was very clear and easy to follow. I'm curious, how long did it take from start to finish to discover the entire exploit chain? Also, were there any parts that you initially found promising that turned out to be dead ends? Thank you.
How long? I can't remember.
Weeks, months, days, hours?
Months.
Any parts you found promising that turned out to be a rabbit hole, a dead end?
Dead ends? No.
Okay. Everything turned out to be an exploit. Any other questions, guys? Nope. Thanks again, Mickey.
Thank you.